Today we're going to look at the tabular method for integration by parts. To begin, let's review integration by parts. Suppose we're integrating a function, h of x, that we can write as the product of two functions, f of x and g of x, and that we know how to differentiate and integrate f and g more easily. For example, if we're integrating x times e to the x, we could obviously choose f of x equals x and g of x equals e to the x, which we can both integrate and differentiate pretty easily. Let g sub 1 of x be any antiderivative of g of x. Then by the product rule, the derivative of f of x times g sub 1 of x is f prime of x times g sub 1 of x plus f of x times g of x. This identity is the foundation of the integration by parts method. Integrate both sides and apply the fundamental theorem of calculus to get the following. This rule is typically written the integral of u dv equals uv minus the integral of v du, where du is not a differential, but instead stands for f prime of x, and dv is not a differential, but instead stands for g of x, so that v stands for the antiderivative g sub 1 of x, and all integrals present are taken with respect to x. That is the integration by parts method. Now that we have that out of the way, what is the tabular method? The tabular method is a shortcut for performing repeated integration by parts. Consider the integral of x cubed plus 2x plus 3 times e to the 2x dx. To begin the tabular method, select our initial u and dv functions. Ideally, u should be a function that has a finite number of non-zero derivatives. If you see a polynomial factor in your integrand, you should select it to be u. That's what we'll do in this case, and dv will choose to be e to the 2x. Next, we create a table of derivatives of u, starting from the zeroth derivative, which is just u itself, in one column. And in the other column of our table, we will store the antiderivatives of dv, starting with the first antiderivative. We stop computing rows of this table as soon as u's derivative is 0 everywhere. The last step of the tabular method is to multiply both entries in each row and sum the results with alternating signs as shown here. Finally, add an arbitrary constant of integration. You can see the result when applied to this example at the bottom of the slide. To finish the video, let's think about why the tabular method works. Suppose we're trying to find the integral of u of x times dv of x dx. Denote the nth derivative of u of x by u superscript n, and denote the kth antiderivative of dv by dv sub k, where we always set the arbitrary constant equal to 0. If we apply integration by parts, we get that the value of our integral equals u dv sub 1 minus the integral of u1 dv sub 1. Next, we apply integration by parts again to the integral in that expression. If we continue in this way, we get this alternating sign sum of increasingly higher derivatives of u multiplied by increasingly higher antiderivatives of dv. There will be a total of k plus 1 terms, where k is the last non-zero derivative of u. And the last term will be positive if k is odd or negative if k is even. On the next slide, you'll see a table that shows the general thought process behind the tabular method. That's all for this video. Thanks for watching.